Our next speaker, who is the CTO of Quadrant Information Security. Joined us for the very first time at SuriCon DC in 2016. We were raffling off a Suricata OISF jacket that were in very hot demand back then. And we had a couple of extras, and I asked the audience if anybody would donate money to OISF to win this jacket or to purchase this jacket. And this guy stood right up and said, "I'll give you $200 for the jacket." So that was the start of a very long and exciting relationship for Champ in the Suricata project. We are so, so delighted. I think you've spoken at every SuriCon since then?
I think I've missed one.
Missed one, but he is a fan favorite. That's why we keep asking him back. So, Champ Clark, guys.
Thank you. All right. Well, thank you very much. Today I'm going to be talking about different ways to store data from Suricata. As mentioned, I'm the CTO at Quadrant Information Security. This last year for us has been very interesting. We were recently acquired by this organization called Workload Partners, who's awesome. They're great to work with. Aside from our team working a lot with Suricata, we develop a piece of software called Sagan. So Sagan is a log analysis engine, and what it does is it uses a rule set very similar to how Suricata uses rules. The rule set's very similar in the way that they look, but it's for examining things like event logs, syslogs, stuff like that. We are also developing a piece of software called Mirror, which I'll talk about today, which is a spooling system for Suricata and for Sagan as well, but for Suricata to put data into databases and places that you want the data to reside in. So you can think of like Elasticsearch and stuff like that. As mentioned, I've spoken at several SuriCons. Me and my friend Brian here started coming in 2016, and after the first one, we were hooked. And so we've tried to make every single SuriCon that we could, because we always get we get a ton of value from not just the Suricata team, but just the community and whatnot. So we just get a ton of value. So we try to come every single year. My talk is going to be talking about, in this particular case, a piece of software called Zinc. What most people do with their Suricata data is they stuff it into an Elasticsearch backend, which is really, really good. It has a lot of advantages to it. So, or OpenSearch. With that, with Elasticsearch, you can do a lot of things like clustering, so you can build these really big machines that take in a ton of types of data. It's a very tunable piece of software. It's kind of like become kind of the industry standard of putting data from Suricata into Elasticsearch. But there are some disadvantages with it, and some of it, some of you may like Java. I'm not a huge fan, but it's in Java. There's some problems that you run into when you have a really large Java VMs with garbage collection and things like that. And as I mentioned earlier, there's lots of knobs to twist. And one problem with that is if you're just getting started with something like OpenSearch or Elasticsearch, that can be really, really overwhelming. And you twist the wrong knob, now you have performance degradation or things like that. And it can be really overwhelming. It's not really ideal for instance, embedded systems, because Elastic can eat just a lot of resources. And of course, as of late, there's been a lot of fun with Elasticsearch licensing around arguments between AWS and Elasticsearch. So with that, a friend of mine brought up to me that there's this new piece of software called Zinc. Now, Zinc is really, really, really new, by the way. I think it came out earlier this year. And the idea behind it is to be a on-disk Elastic-like engine, but to be very, very lightweight, and to have maybe like fewer knobs and stuff like that. So this is where you can go find Zinc. It's over on GitHub. It's actively being developed by Prabhat, who is a really, really nice guy. I've had the pleasure of talking with him a couple of times. He has big ambitions for this project. It uses Bulge as a backend underlying index engine. It looks like a very promising kind of project. As I said, still very, very new. So rather than written in Java, it's written in Golang. It's super light on resources, so CPU and memory-wise. It's also pretty fast. So I mean, whenever we do like a one-to-one comparison, it's probably not up there with Elasticsearch quite yet, but also keep in mind that Elasticsearch has also had a decade or more, actually probably more, of development time, so they've been able to do a lot of tuning. So for what he's done for a fairly short life cycle or lifetime of this project is really, really nice. He's made it really easy to set up, so you can get it set up in mere seconds, which is great, especially if you're doing things like rapid development, where you want to load some data into something, try your software out, and go, okay, that didn't work, blow it away, reload data. It makes it really nice for stuff like that. It doesn't have a ton of configuration options. He's trying to keep it really simple. It does have a compatible Elasticsearch bulk API. So if your software, say you use like Beats or something like that, it's probably going to be compatible with the backend of Zinc. Zinc will act like an Elasticsearch engine to whoever wants to connect to it. It has built-in authentication. It has a web UI, a single binary. It's really nice. So as I said, at startup with no data, Zinc uses just off the top about 60 meg of RAM, which is fairly nice. Now, some disadvantages to this is that while the bulk insert API is compatible with Elasticsearch, the search isn't and doesn't plan on being. The search API for Elasticsearch is super, super complicated. And here's what usually happens. Most people will say, hey, Zinc looks really cool. Can I run Kibana? And the answer is no, because he has no plans on doing that because it overcomplicates the software. But fortunately, he has added in, he has his own UI, and it's pretty nice. There's currently no clustering, so like with Elasticsearch, you can build up these huge, big, machines for indexing data. He's in development of that. I'm not quite sure when it's going to come out, but it should be out probably in the next year or two, which will make it so that you can cluster machines together. And and it's not necessarily a disadvantage, but it's still very new. So just for instance, in the early days, pumping lots of data in, it wasn't uncommon to see it just completely explode into 1,000 pieces as you're trying to stuff a terabyte of data into it. So, but it's getting more and more stable as it goes along. So to install Zinc is fairly straightforward. For one thing, if you just go to Google and Google Elasticsearch space Zinc, you'll come up with his GitHub page. It's also listed here as well. You just find the release that you want, and since it's in Go, you need to find the architecture and the OS that you're interested in. In this particular case, it's current right now is 0.3.4, and I'm pulling it down for Linux for the x86 module. So once you pull it down, you untar it, you make a directory, and then you'll notice the final command here is you have zinc first admin, zinc first admin password. These only need to be a part of that first time run. This is how it sets up the username and password. There's not, everything is almost all environment variable driven. So if you want to increase, for instance, the number of rows that are returned out to you on a search, you would do that at the command line whenever you restart Zinc. So then you start it up, and that's it. You're running Zinc. It's running on a set defined port, which is usually 4080, and you're ready to push data into it. So one of the first things that we decided to do was obviously see how much Suricata data that we could plug into here. Well, to do that, we have to have a piece of software that will push data from Suricata into Zinc. So I'm one of the primary developers of Mir, and Mir is a spooling engine which takes the data, as I said, from Suricata, from the E files, and other places, but from E files, and it'll push it into backends that you care about. So for instance, in Mir 1.0, we still have support for it to pull the data in from the E files and then push them out to an SQL database, similar to how like the old Barnyard 2 software used to work back in the day. In 2.0 in Mir, we no longer support the SQL backend, but it'll push into stuff like Redis or Elasticsearch and stuff like that. Mir is really light on resources. It's written in C. We try to make it, we want it to be usable on almost everything that you can put it in front of. So for instance, on embedded systems, for example. And it's really, really fast. What we also do is we don't just take the data in and then push it into Elasticsearch. We want to augment the data and do some stuff that It would be really too expensive, in my opinion, for it to be done in Suricata. So for instance, doing active DNS lookups on different types of events, we actually augment the Eve. So as the Eve file comes in from Suricata, we'll do a DNS lookup and cache the results and stuff like that so that we can add it to the Eve file. We do the same thing with, for instance, like GeoIP information. If we have a source IP, the e-file is written, there's a source IP address, we can look that up in something like MaxMind's database for GeoIP information to give you the city, the country, and stuff like that. We can also add in things like fingerprinting, which my friend Jeremy Grove here did a talk in 2019 in Amsterdam about. If we see things like MAC addresses, we can look up the hardware. So we can augment the data and add new data to the Eve as it's coming into us. So that's just one advantage that we have. We also have, as I said, multiple different outputs. We can, inputs. Now, we used to only follow a file, but we can now follow not just a file, but we can also read Redis stream, Redis pub subs or named pipes to get the data from Suricata into Mir. Then, as I said, Mir can write out to various different sources. So, for instance, it can write out to another file if you wanted to. Remember, we're augmenting the data. We're adding in DNS. We're adding in GeoIP. So we could write out to a secondary file. We could write out to a named pipe. We can even trigger external programs that you want. So for instance, Mir will get it, augment the data, and then write it standard out to a program that you've written in Python or whatever language that you want. Or it can push it out into various Redis types of data formats. So for instance, channels, rpush, stuff like that. Or into Elasticsearch, or in this particular case, Zinc. Because as I said, Zinc acts as like a Elasticsearch type of engine. So to get Mir, I won't go completely into it. The installation is pretty straightforward. You get it, you run your configure, and then these are options. So enable Elasticsearch, enable Redis, and then enable GeoIP. And the other stuff is pretty much on for default. And then you make install, and you're good to go, right? Now for the Suricata side of things, we can either have Suricata read from a file. You typically already have e-files written out to your disk. So we can have Mir read it into it that way, or we can read it from a pub sub from Suricata as it comes in. So as Suricata is writing to the pub sub, we can have Mir read that pub sub or follow. You can think of like tail-f a file kind of thing. For Mir, but you have to tell it which one you want. So in Mir, basically what we do is we say, hey, I want to follow an E file, for instance. Let's say all my data from Suricata is going into the E file. You just tell it the E file that you want, and then you create this thing called a Waldo file, which is kind of a leftover from the days of the old Barnyard days. What the Waldo file does is keeps track of where it is in the Eve, so that if you restart Mir, that it knows where to pick up where it left off. Or you can tell it to also read in the information from Redis. So in this particular case, we're just reading in from a pub sub of Suricata from Redis. So the data, as it gets written from Suricata into Redis, we just pick it up on the other side, okay? And then finally, we can tell Mir, that we want to write out to Elasticsearch. Of course, we're not writing out to Elasticsearch, we're writing out to Zinc. And the way that we do that is fairly straightforward. We enable the plugin, we give it the URL that we want, and you notice that since there's pre-built-in authentication, we give it the username and password, our batch sizes, everything that we would expect to do in an Elasticsearch instance, we do in Mir, but we're just doing it for Zinc. And then you'll notice the routing down at the bottom. That's the way that we tell Mir what data that we want to go into Zinc or Elasticsearch. In this particular case, you'll see it says alert, files, flow. That list goes on, but allows you to pick and choose. Maybe there's some data that, for instance, DHCP you're not as interested in, so you don't want that necessarily to go into your Elastic or Zinc backend. So you can say, well, just don't output out. So the routing allows you to pick what data goes into the Elastic backend. And then once we get it all set up, we start up everything, and we end up with all these indices. And as you'll see here in the previous slide, we have where it says the index type. So you say Suricata and the event type. You'll see the environment, the variables that are set to how it will create the indices. So once we start it up, we go into Zinc and we say, okay, cool, what do we have here? So as we can see, we have our alert data with current timestamp information, and it does it just like we do with Elasticsearch. Like, there's pretty much no difference. So what we can say is hey, let's go into the Zinc UI. As I said, the Zinc UI is still, as I said, this is still a pretty young project, but it allows us to go in and create visualizations similar to how Elasticsearch does. As I said, it's not as advanced, but they're trying to keep it simple, which I kind of respect that. So in this particular case, we're showing, the timestamps, the app protocols related to certain flows. I'm pulling out the GeoIP information, and I happen to be pulling there's some metadata flow bits. And we can basically create these kind of searches that we would expect to be able to pull out of Elasticsearch. So here's our TLS data, the SNI, more GeoIP information, TLS version, stuff that we do every day in OpenSearch, right? And alert data, of course. So creation dates, stuff like that. So we can create these nice little visualizations. It doesn't require very many resources because, as I said, it's written in Go. It's pretty resource friendly. So we get done with it and we think, okay, that was kind of fun to do. That was pretty easy to set up. So we were stuffing in, we had a customer of ours who had a 10 gigabit connection, and we were just stuffing Eve in there, just seeing if we could get it to blow up. And it handled it very, very well. So Zinc was able to keep up with the load. But then this got us thinking, what else can we do with this type of data? So one thing that we came up with was a thing that actually my friend Brian came up with. The name was creating network data points. Basically something that you can search through in the event that you have a compromise or you want to search for indicators of compromise. You can think of this as a non-repetitive data collection system. And I'll try to explain it here. So here goes the problem. We need to search a ton of Suricata data. And in our cases, we have just, our systems have 90 days or more Suricata data on it. And usually the question that comes up is we need to search for an IP address or something like that. So this data has everything from file hashes, IP addresses, JA3, or TLS connections, file names, all kinds of stuff. And the solution is that you could have this really kick-butt Elasticsearch system that, you have just 64 nodes and a petabyte of storage and all this great stuff, so you have access to all this data very, very quickly. But the problem is that to have this kind of kick-butt Elasticsearch cluster for all your Suricata data it's pretty expensive for the average company. It's not just expensive for the resources, CPU, stuff like that. It's also expensive just for continual feeding and maintenance of this big machine. It's not really possible for a lot of organizations to do at that kind of scale. What I did is took a picture of a slide from General Motors. This is their General Motors from, I can't remember if this was 2020, I think it was, or yes. It was the Boston SuriCon. As you can see, they have the facilities to do this. So they have this huge 1.2 petabytes of storage. They have 200 network sensors out in the field reporting to it, 120 data nodes. And just the care and feeding of this machine, basically this huge Elasticsearch indexing system, is a lot. And it's not what you can expect every single, especially mid-range customer to be able to support. And that was a really great talk, by the way, that they gave. It was really neat to see what they were doing at that scale. But the problem is that costs a lot of money. What we typically find is, and this is the way that we do it in many cases, excuse me, not this one, the third one, but some people just spool the data out to disk and they say, you know what, I can't afford to do, or I don't have the resources to do everything into Elasticsearch. So what I'll do is I'm gonna spool it out to a bunch of files and I'll just grep the files whenever I need it. What's really good about that is that you can archive a ton of data for a long amount of time because Eve compresses very, very well. So storing a year of flow data and all that kind of stuff becomes possible at that point. But during an incident, retrieving the data is super, super slow. You're going through and you're doing greps and they take forever, right? And it doesn't work. So the third way in which we see a lot of our customers use it is kind of a hybrid solution where they have a cold storage system where maybe they store Suricata data for 6 months, so that's in it's gzip compressed, stuff like that. But they also use Elasticsearch, but only for, say, a month or 2 weeks. They use it for a shorter range of time. So this can be more cost effective. You can do, especially if you have an incident that's really, really fresh, in Elastic you can go through and pull that information very, very quickly. But if it gets over a certain amount of time outside of your Elastic threshold, then of course you're going back to the grep system that you have. And this is what we see a lot of organizations do. Once you get outside of the Elasticsearch scope, of course, your data searches get slower. And we see this happen a lot where customers will say to us, is I want to see an IP address in the last 6 months, and that's where the searches get really, really slow. So what I got to doing was thinking about, well, maybe there's some sort of bridge in between those modes. So using Zinc to build predefined network data points for really large IOC searches. So you can kind of think of it as a system where you're just recording single pieces of information about particular pieces of data, which I'll get more into. So the question comes up, the customer calls. They say, hey, have we ever seen this IP address or hash or whatever it is in the last year in our network? And the thing is that in a lot of cases, you're going through and you're having to grep through a lot of data because they don't have the resources. And what we're really trying to get to is a yes or no question. Yes, we have seen this go this way, or no, we haven't, full stop, right? There shouldn't, so it's really, so for instance, if a customer calls up and says, hey, I want you to find out if we've seen this IP address in the last year, and we grep through, a year or terabyte of data just to get to a no answer, we still took forever just to get to that no answer. We should be able to get to that no answer fairly quickly, would be ideally. So what we decided to do was try out this idea of building out network data points. So here's what I mean by non-repetition. So there's some data that we'll always keep. So this is the set of data. So for instance, timestamps, flow IDs, source IP, destination IP, stuff like that. We're going to keep in basically a smaller data set. But to further distill it, and this continues on with that. So there's some information that we're going to keep directly from specific types of flow data. So for instance, as I said, flow, source and destination, file information, hashes, file magic, file names, TLS, DNS, stuff like that. So different types of things that we're going to pull out of there that we're going to keep. Keep in mind, we're not keeping the entire data set from the Suricata E. We're breaking it down. We're distilling it into just the things that we need to make rapid search for in the case of a compromise so that we can do a fast data search. So we're only trying to keep the unique data that we're interested in. Then we use the unique data that we have to make predictable IDs inside of Zinc. Or this should work in Elasticsearch as well. So basically what we're saying is there is a IP address, let's just call it an IP address to keep it simple. There's an IP address that we're interested in. We'll take that IP address and make a hash out of it, an MD5 hash, and we're going to use that as a document ID because it makes it now a predictable document ID in the future so that we can store that IP address or that file hash only one particular time, which I'll kind of get to. So in order to make the predictable IDs, what we do is, for instance, with the flow data, we hash either source or destination, only the side that we're interested in. If it's internal traffic, I might not be interested in that. I might want my IOC search is probably looking for something external coming in. If I'm looking for TLS data, we actually hash the J3, the J3S to make one new unique ID. And this again, these IDs are going to be used for the document IDs. For SMB, we do some other stuff with SMB, which I'll get into, but it's the SMB command and the file name. For HTTP, it's the full URL. So for instance, just to kind of back up, let's say that somebody goes to a URL. The question again is, has somebody been to this URL? It's not meant to tell you, these are all the people who went to this URL. It's supposed to say, yes, I have seen somebody go to that URL. That's pretty much it. So we use that as a mechanism so that we store the URL, but we only store it once with the last flow ID that we saw it. Same thing with like FTP, DNS information, we just hashed our name that's returned on queries because we only do queries. So the idea here is that it gives us predictable IDs that we can do. So as we see a URL, we can just update that one record over and over again. So so we automatically end up dropping the repetitive data. So if you see a URL or an IP address that's external 100 times, I don't need to record it 100 times in this particular case. That's all in my flow logs, that's all in my Suricata data, which I can pivot to. This is just to say, yep, I've seen that URL, that IP address, that file hash before. So from a Suricata configuration side, this is on the, we don't need all the really technical GUI details that you can really get into with Suricata. So what we're doing here is we're saying, hey, we just want to push this information. There is some TLS extra information that we want, but from flows and files, you can just keep that your default output and just hand it over to Rebus and publish it to a subpub called, or a pub sub called Suricata. So it's going to continually push this data into it. And then from the mirror side, we would read that pub sub. But then in mirror, we'd also tell it too that we want to do network data point collection. And this is kind of a new thing. It's super kind of experimental. But what we're saying is we want to enable network data point collection. The ignore networks is really important because a lot of times if I get an IOC request, or it's usually related to an FBI flash report or something like that. It's like, have you ever seen this external IP address hit our network before? So we want to make sure our ignore networks is very well defined, because the better that we define that, we'll drop more data that we don't necessarily need to see. So for instance, not just your internal networks, but your external blocks as well. Or if you're a big Azure user, AWS user, you may want to put those network blocks that you use in there as well, so that you can drop a lot of the data that you don't necessarily want to see repeatingly. And then you'll see the NDP routing. This is the data that we want to pull, or this is the flows or eaves that we want to pull the data from. So for instance, file info, TLS, flow data, stuff like that. And then we can also say, hey, when we see SMB commands that are related to create files or write files, we want to record those. You'll notice we don't do reads. There's a lot of reads in networks, but what we typically find when threat actors are pivoting in networks, they're writing more files. So this gives us a list of, here's all the files that have been written within your network. Of course, you could add to that command if you want. We've also seen things like, believe it or not, FTP used for exfil, especially on ransomware type of attacks. So this gives you everything that we have or that we need. So for instance, if somebody's pushing data out from via FTP, it might not getting the data, we're probably maybe not as interested in, but pushing data out. So we just saw a group called Black Basta who was pushing data. They use a piece of software called rclone, which is the FTP client basically. So the idea here would be, why am I doing all this new FTP stuff? And then the final one here is where it says SMB internal. So again, threat actors we see move files within a network through SMB a lot. So there shouldn't be too many internal to external SMB connections, right? So the idea here is you can flip a flag and say, you know what, I want you to record all SMB internal traffic as well. Most internal traffic, for instance, as I said, if we're looking for an IP address, it's typically not a 10 address, it's some external address that we're interested in. But from an SMB standpoint, since threat actors, after they compromise the network, they use SMB to push files around the network a lot of times, we want to record that internally. So it's really about threat hunting and stuff like that. So then our question becomes, have you seen this IP address in the last year? And we can say, yes, you know what, we have seen this IP address in the last year, and the last time we saw it was at this time and at this timestamp. Now, if you're using that cold storage system, you have a time to start looking at. So if it happened 4 months ago, I don't have to search through all the previous months to get to that 4 months. I go right to there and then start working backward. It'll make sure search time's less. Or if we say, no, we didn't see that IP, I don't have to grep anything. I don't have to go into Elasticsearch, I don't have to look at anything just because I already know the answer is no based off of a very smaller data set. So if you're making these tables in Zinc and it's non-repetitive data, your data storage actually goes down quite a bit. Now, granted, you're not getting the full visibility as you would if you were pumping everything into Zinc, but that's not what we're doing here. We're trying to make non-repetitive data. So just for instance, whenever I took a 128 gig spool file and fed it into Zinc, it would normally consume about 500 gigabytes in storage on the Zinc side, that is. You push the 128 gig into Zinc, just like you would, that's everything, and you would usually get about a 500 gig data store for just Zinc data. But now, if I was just taking the non-repetitive data, the data that I just want to care about in those really quick searches, if you think of it that way, and store it, it dropped that Zinc storage down to 600 meg. That only makes it super fast to search, but you can get those answers really quickly. But it's not, you're not storing every little piece. You're only storing just the individual pieces that you want to see. And what that gives you is, so for instance, here's my TLS connections. On this particular one, it looks like we're looking at SNI version and the issuer ID. This is just like a generic search. But this is every SNI that we've seen in this particular network and the versions, stuff like that. So if I say, hey, have we ever seen a TLS connection to Facebook, I can go in and just look it up real quick. I don't have to grep through tons of data or have an Elasticsearch backend that might have to go back really, really far. But Like with Elastic, you can do more advanced queries. So you can say, hey, show me all, out of your network data points, show me all your DNS data that has a RR name, a query name that was returned with star.ru. So you can see all your DNS queries, stuff like that. Here's what the data kind of looks like. I don't know if you can completely see it there. Sorry, it's so small. But as you can see, the data sets are really, really small. We're compacting them because we're dropping a lot of the data to the floor and saying, look, we've already got this data in Suricata E files. We might have it in our Elasticsearch backend. We know we have the data. That's not the data we're trying to capture here. We're only trying to keep the data that will answer specific questions that we have. So that's kind of what the data looks like. So you'll see it's very, very stripped down. Just a little bit of GeoIP information, the query, stuff like that. You can also say, for instance, if I'm doing threat hunting within an environment, I might pivot to this data and say, hey, show me all the TLS connections that use certificates from Let's Encrypt. And then go through it and say, do any of these stand out to me? If I find one, I can click on it and say, okay, that one looks interesting to me. Grab that flow ID and then pivot to another point. And that point could be in cold storage, which is slower, but now I know at least where it is, where it was last seen. Or I might be able to, if it's recent up, maybe I can go into my Elasticsearch backend. But the idea, it gives you that pivot point. You can also look for file information. So for instance, file hashes, stuff like that. So here we're looking for all executables with the file name of hash. I should point out too, on the top there is actually, that is what I'm entering into Zinc. So that is the query syntax that it is. So again, it's good for looking through our IOCs that are related to possibly an incident, or if you just want to do some generic threat hunting and just kind of go through and just quickly look at like, what were my SSH connections and what were the client server types of every SSH connection that I've seen within my network. Or the interesting ones, I should say, which I'm doing here. So basically we're saying, hey, I want to know all the SSH connections where the client software is libSSH. You know, we typically see this, and for instance, everybody who's scanning the network, internet, doing brute force type of attacks. So this is all the IP addresses that we've seen that were using libSSH, that were unique to us. Or if I say, hey, we also have another index which is just user agents, just unique user agents. So I can go through and say, hey, show me every user agent that has the word help star, hello star. And as you'll see, we have a couple here from Hello World. And these are obviously people scanning for low-hanging fruit. But it'll give me the IP address and the unique time that it solved them. Same thing with SMB. Now again, with SMB, I can actually, if you flip the flag, it'll do internal to internal traffic. So it'll show just the right information. So in this particular case, I'm looking for all SMB traffic that's being written across the network that has the word agent within it. So for your yes or no answers, you can answer them super, super quickly. You can basically go through here, say, okay, I have this really small data set, look through it very, very quickly, and then pivot to maybe something that takes more resources, but it gives you it gives you a mechanism to point to the right place for those yes or no questions. And that is pretty much my rundown. If anybody has any questions, I'd love to take them. No.
I like what you've done with minimizing data, but can you use Zinc? Can it do faceted or group by type queries as like a mini replacement to Elasticsearch for small deployments? Do you know?
To be honest, I wouldn't really know the answer to that one. It's still pretty limited on the query. The good thing about Prabhat is that he is publishing the APIs, he's going along and whatnot, and it's coming along quite well, but it's still fairly limited. But it's coming along really well.
Yeah, I'll be keeping my eye out because Elasticsearch can be a pain for just home use and stuff.
It's also one of those things too, like where as a developer, setting up Elasticsearch and then tearing it down and setting it up, it's just not really feasible. Whereas with this, I mean, you literally are starting it in like 5 seconds. Like I can just hit Control-C, delete the data, hit up arrow, and then start up Zinc again, and I'm rolling again.
And all that NDP hashing, you're doing that in Mir?
That's all being done in Mir.
Okay.
Yeah, so we're taking all the data in and then keeping just the things that we want, hashing it, and then making a unique ID within Zinc.
Okay.
Any other questions?
Hi, so do we have any capability that we can correlate that data with the flow ID or some hash ID with other modules of application, maybe proxy, or see where the other data is coming from for that particular source IP or destination IP.
So all the data is stored with the source and destination IP, but it could be overwritten if multiple times it's happening, right? So it only keeps one record of the event. So for instance, if it was a IP address and there are multiple people writing out or going to that IP address, it's only going to keep one of them. It's just saying, this is the last time I saw it, so that you can go back to the last flow ID and then find the data back from there. So it will keep some of that, but the idea was also to make it so that we're only keeping limited sets of data. If we start adding in too much, then we just end up back at a system where we're storing everything back into Elastic. And we think that's already being, or in Zinc, that's already being done, or might be already being done. And then it gives you that pivot point. So we're trying to come up with a means, so for instance, a lightweight system for our IDS boxes, for instance, where they only have, say, 32 gig of RAM, and that's using for everything, that we could have the small index for our SOC to go through and say, where's this IP address? Oh, it's right here. It's over in this hash, and then pivot and go into that to grab those like really more detailed information about that particular event. I should repeat the
That's
question.
better, great indeed. Thank you, that was really interesting. I've got a question, I may have missed that. Are you storing the initial timestamp, the new data has been seen?
Oh, so you mean like the first instance of it?
Yes.
So that's a great question. So the question was, are we storing the first instance? So the idea would ultimately be this is the first time that we saw the IP address and the last time we saw the IP address. So that was a little bit of a problem, and I chose just to keep it with the last information. The reason is, since I have predictable IDs, I can go in, when I update the stuff in Zinc, I already know the ID field, right? In order for me to keep that, I would have to do queries against the database and say, hey, have you seen this? Okay, remember this. Now store the updated information, which cost a lot more in CPU and cycles and stuff like that. So I would have liked, I could never come up with a good way to keep that first impression of information, so I chose just to keep the last, as the last one's where I'm going to start my searches at anyway. But yeah, really good question. Thanks.
Hi.
Hi.
My question is more for Mir. So, as you mentioned that it is taking the reference input as eve.json. So, do we have options to have more data logging coming in? Not JSON files, but syslogs, or we have a lot of data coming in our system. So, does Mir support other formats as well?
Does it store other formats as well? I'm sorry.
Like syslog, not a JSON file,
Oh.
but a simple syslog that I
mean-
would like to, again, as a correlating,
Yes.
I would like to put it in the same place. So does it do that?
Yes, so I think the question kind of is that can Zinc handle non-JSON information?
That's right, yep.
So like with Elastic, on ingestion, it needs to be in a JSON format. Most syslog engines like syslog-ng and our syslog will take your traditional syslog data and convert it into a JSON format. The issue is, and then we saw this, we tested it with logging, and logging can be so dynamic. So you have Windows events who have a ton of keys in it, and then you have other events that have very little, like standard firewall stuff. At that point in time, Zinc exploded into 1,000 pieces because this data was just incredibly crazy dynamic. It's probably a lot better. I haven't checked it in probably 6 or 7 months. With Suricata, the data is kind of structured in a way, so I think it's really good with that. I would suggest just giving it a try. I know that other people are working with Zinc to store log data. I would imagine it's come a very, very long way. But other than just giving it a try, it would probably work fine.
My question is around the use of flow ID,
Yeah.
and comparing it effectively, I guess, to the community ID. I found that the flow ID is kind of localized
Yes.
to Suricata, as well as it's unrepeatable. So if you take that same PCAP and run it multiple times, that same flow will actually have multiple flow IDs.
Correct.
And so can you kind of explain the use of flow ID as opposed to community ID, which you can pivot on within Wireshark, et cetera?
So the community ID would work really well with the flow data, but for instance, like with file hashes and stuff like that, where I'm saying, I want to know if this file has been seen in my network. The community ID doesn't really help me there. It is a good idea. So for instance, maybe in the future, we might make it more of an option thing to say, hey, rather than storing the flow ID, maybe we could store the flow ID with the community ID where it's available. I don't see any, actually it'd be really easy to do, to say if I have a community ID and it's available, give me both. It currently doesn't do that, but that'd be super easy to do and probably a good idea.
All right, just second question. The use of MD5 on, I'll call it like a full object. So you give the example of like an HTTP request. So I assume that's like domain plus URI kind of a thing?
100%.
So do you have any concept or ability to do like a contains query? So maybe breaking apart that URI into, here's the path and then the resource at the end of that. And that way you can kind of build contains logic within your searches.
No, that's a good idea. As it stands right now, you're 100% right. It takes the hostname and the URI and combines them together to make that hash. So in the traditional E file, it is broken up. But at the time, for this particular project, I hadn't seen it, looked at it that way. It might be a good idea to maybe do both. So basically, I'm storing the MD5 as the host name and the URI, but then break it out so I can do more queries, kind of like you were discussing. Yeah, but it doesn't currently do that. Yeah. Well, thank you very much, everybody. I really appreciate it.